Hi girls, this is video 19 of the walkthrough for our topic 2 notice rates of change and differential equations. This is the 19th and last video because this brings us to the end of the subtopic modelling motion. And the last thing we have to talk about as per the syllabus is simple harmonic motion. Let's talk about simple harmonic motion before we look at any maths. What's the definition of it? Well, if you're talking about 2 points in a straight line from each other, now they use A and B in this diagram, which is unfortunate because A we use for something else very shortly. So let's call these points C and D instead. So we have points C and D, and imagine that there's some sort of object that is moving between the 2 points in a straight line. Between them there is a middle point, which for convenience sake we usually say is the origin. Now this point is moving with acceleration so that it's directed towards a fixed point, usually the center or the origin on that line, and is proportional to the displacement from the fixed point. And then the particle is said to move with simple harmonic motion. What does that mean? Say that I've got a particle that is moving towards the point D with displacement of x in a positive direction. Now all the time it's moving between the origin and the point D, it's slowing down. So much that by the time it gets to B, its velocity must be equal to 0, because before it can go back towards C, it's got to stop. Now, once it gets to the point B, we say that its displacement is a certain amount. Guess what we'll call it? We'll call it A for amplitude. Now, when it gets to B, it's got to stop and then move back towards the center O and then back towards point C. Now, to do that, if it's slowing down all the way between the center and the point B, its displacements, rather its acceleration, must be working in the opposite direction to the displacement. Yeah, makes sense. If it's got to stop at the point D and then move back towards the center again, all the time it's got to be slowing down. So the acceleration is moving in the opposite direction to what its displacement is. Now, by the time it gets back to the center, the velocity of the object must be at a max. Now, the acceleration is still working in opposite direction to displacement. At the center, its displacement would be 0. Now, all the time that it's moving from the center out to the point C, again, the displacement we're saying is in might be x, of course, but it's in the opposite direction to what it was on previously. So the acceleration, the displacement would be negative x in that direction. Now, all the time, again, as it's moving from O to C, it must be slowing down. So again, the acceleration in that case would be moving in the opposite direction to what displacement would be. So in that case, it would be a positive direction. By the time it gets to C, its velocity again would have to be 0, because to be able to stop there, or rather to be able to turn around and come back, its velocity must be equal to 0. And at the point C, its displacement would be negative A, where A is the amplitude. Now, the other thing about simple harmonic motion, as it says, is that it is proportional to the displacement from the fixed point, i.e. the center. So we have this d squared x dt squared, which we know is acceleration, or if we say it's the second derivative of displacement, is proportional to negative x. Now, negative because it acts in the opposite direction to what acceleration is. So if I change that proportionality symbol into an equation, I can say that d squared x dt squared, the acceleration, is equal to negative kx, where x is positive. X is displacement, and k has to be greater than 0. Now, for convenience sake, from now on, we're going to change k, the constant of proportionality, into the lowercase Greek symbol omega, which looks like a funny W but squared. We square it because later we might want to find the square root of k, and getting the square root of w squared is a bit easier than finding the square root of k. So on that basis, if d squared x dt squared is equal to negative kx, where the center of our 2 points that they move between is at the origin, then we can go on and get these formulas for simple harmonic motion. Now, the first one. So if acceleration x dash dash, which we know is equal to acceleration, and we know acceleration is dv dt, and we know dv dt is according to the chain rule dv dx by dx dt, and we know that that is equal to dv dx by v. Starting with this bit here, if I know all of that is equal to negative omega squared x, then I can change this differential equation into this for velocity. Velocity squared is omega squared by a squared minus x squared, where a is the amplitude, and the value of x goes between a and negative a. Now, you are differential equation goddesses by this stage, so I'm quite confident that you can take this here and change it into this relationship for velocity, or velocity squared. Try that in your own time. See if you can take this relationship here, dv dx by dv, equal to negative omega squared x, into this relationship. I'm sure you can. Now also, if we know that the acceleration d squared x dt squared is equal to negative omega squared x, and I know I can change it into this relationship, I can change this relationship and get v by itself. V would be the square root of omega squared, a squared minus x squared, or just plain old omega. Again, get the square root of omega squared is omega, by the square root of a squared minus x squared. Now v, of course, is dx dt. And if we're saying that's equal to omega by a squared minus x squared raised to the power half, then there's another differential equation which you can rearrange to get x in terms of t. Now when you do that, you get this relationship. X is equal to a, the displacement, by sine omega t. You get x is equal to a sine omega t plus alpha. Or if you had it as a cos function, displacement x would be equal to a, the amplitude, by cos omega t plus b. T is time, and alpha and beta are just constants of integration. Okay? Values for c, in other words. Now, if we start, if t is equal to 0, which is what this indicates here, if t is equal to 0, and the displacement at t is equal to 0 is equal to 0. In other words, initially, if the particle starts at the center, then the values of alpha and beta, these constants of integration, would be equal to 0. So x would be a sine omega t, or x would be equal to a cos omega t. Now again, I'll leave you that to find for yourself. A is the amplitude, and one final thing that we can use here for our formula is this. T, we know, for all time has referred to as the period, the time it takes for one complete oscillation. We know that from way back. And we know that t is equal to, or previously we know t is equal to 2 pi on the frequency. Well, in this case we're saying for simple harmonic motion, t is equal to 2 pi on omega. Now again, what's omega? Omega is the square root of our constant of proportionality that we got from the very start, k. And Also, again, frequency we know is 1 on the period. Okay, frequency per second. How many little bits cycles can it produce in one particular second? Okay. Now, all of those formulas there are on the formula sheet, and they can be all referred to. So, having that handy, the formula sheet, we can go on and do these examples. Starting with this one. An object is moving with a simple harmonic motion, good, where the period of motion of the object is 5 seconds. So straight away we can say that t, the period, is 5 seconds. And we already know that omega is equal to 2 pi on t. That's one of our formulas that's on the formula sheet. So therefore, omega is 2 pi on 5 in this case. Let's go on. It says if the velocity of the object when passing through the origin through x is equal to 0 is 15 meters per second, calculate the amplitude and acceleration at the furthest point. Well, the other thing that's given on the formula sheet is this one that we know for v squared. V squared is equal to omega squared by a squared minus x squared. A is the amplitude, x is the displacement. Now we're told when x is equal to 0, the velocity is 15 meters per second. So they sub that in, 15 for v, 15 squared is equal to omega squared by a, the amplitude, which we don't know, but we're trying to find, minus the displacement, which in this case, when the velocity is 15, displacement is 0. 0 squared. So the other thing I meant to put in was omega. We know what omega is. It's 2 pi on 5. So 2 pi on 5 squared by a squared minus 0 squared is just plain old a squared. Alright, so if I was to rearrange that, a squared would be equal to 15 squared times by, okay, the reciprocal of that, 2 pi and 5, which would be 5 on 2 pi squared. So what would they make a? Well, a would be the square root of 15 squared, which would be 15, times by the square root of 5 on 2 pi squared, which would be 5 on 2 pi. Or, that would be 75 on 2 pi. Now, the velocity was in meters per second, so I'm confident saying the amplitude would be 75 on 2 pi m meters. And I will also be confident saying that if I've got a squared is 15 squared by 5 on 2 pi squared, a would be plus or minus, which we don't mind in this case. The amplitude would be either side of the center. So it could be plus or minus m. Plus or minus 75 on 2 pi m. Okay, that's the amplitude found. What about acceleration? Well, the other thing that's on our formula sheet is acceleration x dash dash is equal to negative omega squared by x. So we know what omega is. We just worked out it is 2 pi on 5, and that is squared. And we're talking about the acceleration at the furthest point. Well, at the furthest point is where x is equal to a, the amplitude. So subbing into that, 75 on 2 pi, 75 on 2 pi for x, I can work out what the acceleration is. All comes to negative 2 pi by 15, or negative 30 pi up. Now its acceleration is meters per second, or meters per second squared. The negative just indicates that it's in the opposite direction of what displacement would be. Excellent. Let's go to the next page. moving with simple harmonic motion at a velocity of 6 meters per second and 4 meters per second, respectively, when it is 2 meters and 3 meters from the center. So, the further it is away from the center, 3 meters, it appears to be slower, which we know would be the case because by the time it gets to its amplitude, A, that total distance away from the center, its velocity was supposed to be equal to 0. So further away it is from the center, slower the object will be moving. Find the amplitude of the motion. Well, again, we can use, we've been given some velocity, so again we can use velocity squared is equal to omega squared by A, the amplitude squared, minus x squared. Try and find the amplitude of the motion. So the initial, in the first case, it was moving at a speed of 6 meters per second, or 6 squared, which would be 36, is equal to omega squared by A squared minus A squared minus, now that's happened when it is at a displacement of 2. 2 squared would be 4. Equation number 1. Because using the other bit of information, we're told when its velocity is 4 meters per second, or 4 squared is 16, it equals omega squared by acceleration squared at a displacement of 3. 3 squared would be 9. There's equation 2. Now both of those can be arranged to get w squared by itself. So if I can do that, I can get one single equation with only A, the amplitude, as the unknown. So 36, or w squared would be equal to, from equation 1, 36 on A squared minus 4. And from equation 2, w squared would be equal to 16 by A squared minus 9. So here's my one equation with A only as the unknown. So if I rearrange that, on the left-hand side, I would have 36 by A squared minus 9, and the right-hand side, I have 16 by A squared minus 4. Okay, expand the brackets, that would be 36A squared minus 324, would you believe? 36 by 9 would equal on the other side 16A squared minus 64. Okay, rearranging that, getting A squareds all together on one side, I'd end up with, on the left-hand side, 20A squared. And on the right-hand side, that would leave me with 260, which would make A squared equal to 13, which means that I could end up with a amplitude of plus or minus square root of 13. Yay, cracked it. There's A. What about the period? Well, again, what do we know the period is? Well, the period is equal to 2 pi on omega. So to find the period, we'll need omega first. Now, can we do that? Well, yes, we can, because if I take equation 2, for example, which says 16 is equal to omega squared by A squared minus 9. Now I can put in my value for A, which was 13. So 16 is equal to omega squared by A squared now becomes A, which is root 13. So that would become 13 minus 9. 16 would be equal to omega squared. 13 minus 9 is 4. That would mean that omega squared would be equal to 4, or plain old omega would be equal to 2. Now, I hear you all saying, what a plus or minus? Well, remember, K should be positive. We were told that initially, K should be positive. So that means that omega squared should be positive, which means that omega should also be positive. So rather than saying omega is plus or minus 2, we're just going to go with omega is equal to 2. And if that's the case, remembering that the period is 2 pi on omega, and we've just worked out that omega is 2, that would mean that the period is equal to pi. Excellent. Finally, What's the time taken between the 2 points, i.e. when it's 2 meters from the center and 3 meters from the center? Well, remember one of the things that we said, that x is equal to a psi omega t. Now, we're going to assume that at t is equal to 0, x is equal to 0. So assume that when t is equal to 0, x is equal to 0. Now, if we can do that, we can say, therefore, x would be equal to a sine omega t, without any plus alpha, alpha being a proportionality, a constant of integration. We don't need to use it if initially t is equal to 0, x is equal to 0. So x is equal to a sine omega t. Now we know what a is, amplitude, it's root 13. And we also know what omega is. It was 2. Okay, so t being time. So if I rearrange that, I can get t by itself. Let me just cut to the chase better enough. So x on root 13 would be equal to sine of 2t. And if I went inverse sine of x on root 13, that would be equal to t, or t would be equal to a half inverse sine of x on root 13. So I need to find some values for t given some values for x, and I do have some values for x. We were told we want to know the time taken between when x was 2 meters from the origin. When x is equal to 2, t would be a half of inverse sine of 2 on root 13. Best to put that in radians, of course, than the calculator. Now when you do it, it comes out as 0.294 seconds. Now the other displacement we're interested in is x is equal to 3. What's the time when it gets to 3 meters from the origin? Well, again, we just take a half inverse sine of t on root 13, where t is time. In this case, when x on root 13, when x is 3 though, so it's 3 on root 13. Put that in the calculator with mode and radians. It works out to be 0.491. So it takes 2 seconds to get 2 meters from the origin of 0.294. It takes 0.491 seconds to get 3 meters from the origin. How long does it take to get between the two? Well, time taken would just be the difference between the two. So time taken to get between the 2 points, 2 meters and 3 meters respectively from the origin, would be 0.491 minus 0.294, gives a grand total of 0.197 seconds. Sweet. Alright, last example. Is moving on the x-axis. Its speed is given by this. V squared is 40 plus 30x minus 10t squared. Show that it is in simple harmonic motion. So why would they give something velocity in v squared? The reason being is because of the relationship that we know acceleration can get into. Remembering that acceleration is dv dt, and we know dv dt according to the chain rule is dv dx by dx dt, and we know that dx dt represents the velocity, so we've got dv dx by velocity. Now here's something we haven't struck up a conversation about quite as much yet, but think about velocity. So I've got dv dx, but velocity, would it not be the derivative of a half v squared with respect to v? Think about that. The derivative of a half v squared with respect to v, wouldn't that not be v? Yes, it would. So to this stage, I've got dv on the top, dv on the bottom. So that means that I can take acceleration and say that it ends up being this, the derivative of a half v squared with respect to x. Yeah. Again, you'll find that on the formula sheet. Now, why do we go through all of that? Because they actually give us v squared in this case. So if I've got v squared, I can find a half v squared. A half v squared would be equal to half of 40 plus 30x minus 10x squared. So it would be 20 plus 30x minus 5x squared, not 30x at all. Sorry about that. It would be 15x. And remembering what we just said, acceleration is equal to the derivative of a half v squared with respect to x. That's crazy. Do we have half v squared in terms of x? Yes, we do. Half v squared is 20 plus 15x minus 5x squared. So if I find the derivative of that with respect to x, I get 15 minus 10x. And if I just do a little bit of a flim-flam on that, if I was to factorize this and take out negative 10, I'd be left with x minus 1.5, would I not? Now if you, so let me just summarize that. Acceleration would be equal to negative 10 x minus 1.5. Yeah. Now if you compare acceleration in terms of simple harmonic motion, which is negative x is equal to, acceleration is equal to negative omega squared by x, then these two compare pretty well. That means that omega squared is equal to 10. And the difference between x is 1.5 and x is that in just this case, the center is equal to the origin. In this case, the center is not at the origin. The center is equal to, the center between the two extreme points is at x is equal to 1.5 meters. But because we can compare them favorably, we say, therefore, because this acceleration equal to negative 10 x minus 1.5 compares favorably with this version of acceleration, negative omega squared x, we say, therefore, it is simple harmonic motion. Done for the first bit, we've shown that it is simple harmonic motion. Okay, so that was our A. What about B? Determine the mean position, the amplitude, and the period. Yeah, which means find everything. Well, okay, again, what do we know? Well, comparing our equation, acceleration is equal to negative 10 x minus 1.5. We know that the 10 outside the brackets is equal to our omega squared. So that means that omega is equal to root 10. And we're asked amongst this to find the period. We know that the period is equal to 2 pi on, 2 pi on omega. Come on, 2 pi on omega, which we just worked out as root 10. So the period is equal to 2 pi on root 10. Okay, that's the first thing we had to find, the period, 2 pi on root 10. Now we can rationalize that, I'm sure you can. But let's go at the next little bit of this to work out the other thing that I have to find. It does say mean position, so what does it mean by that? Well, from the formula again for this particular case, which is the acceleration is equal to negative 10 x minus 1.5. Okay, straight from that we can read what the mean position is. Mean position is just where the center between the two extremes is going to be in a straight line. So, and as I just sort of mentioned before, the mean position, the center is not at the origin, but at x is equal to 1.5 from this bit over here that we know there. So there, we've worked out mean position now as well as the period. Okay, what else? The amplitude. Now, at x is equal to a, the amplitude, what do we know? Well, at that extreme location, we already know that for a simple harmonic motion, when the displacement is equal to the amplitude, velocity is equal to 0, because it's got to stop before it can come back. And if I put that into my v squared, in this case, which is equal to v squared is equal to 40 plus 30x minus 10x squared, and if v is equal to 0, then 0 squared would be equal to 40 plus 30x minus 10x squared. Or if I rearrange that, 0 would be equal to negative 10x squared plus 30x plus 40. Guess what that is? That's a quadratic equation. My goodness, we can solve that using our GC. Using Polyschmolk 2 on our calculator, in other words using GC, we can work out that x is going to be two things when its velocity is equal to 0. X is negative 1, or x is equal to 4. Now think about it. X is equal to 1, x is equal to negative, x is equal to negative 1, x is equal to negative 4. Those 2 points represent where velocity is equal to 0. In other words, the extreme of our movement. So, what does that make the amplitude? Well, if you were to take the amplitude, which would be take the extreme 4 and take away from the mean position, which we know is 1.5, the amplitude would be 2.5. Or I could do the same thing again. Amplitude would be taking the 1.5 minus the other extreme, negative 1. Still works out to be 2.5. Or the other way we can do it is, as we've done it previously, take the max, which is 4. Take from that the minimum, which is negative 1, and divide the whole thing by 2. 4 minus negative 1 is 5. Divide by 2 gives us an amplitude which we already know is 2.5. So there we have the last thing that we're asked for in this particular question, find the amplitude. Alright, that's the end of this video. And that's the end of all these videos. Thanks for listening, girls. See you soon.